Billboard serves many purposes in modern computer graphics, mostly as a way to save computational power, but also for UI purposes such as floating health bars and character names.
When creating computer-generated scenes, it is important to keep in mind the balance of quality to processing power needed to render it. When doing images and sequences, it's a question of time for the renderer, but when rendering in real time, the balance comes down to whether the scene is smooth or becomes more like a slideshow, or maybe even makes it impossible for the computer to keep up.
Therefore, solutions such as billboarding becomes very important to lower the taxation on the processing power in places where a less heavy stand-in can allow for the power to be redirected elsewhere, usually to places that are more obviously noticeable to the viewer. The implementation of billboarding and imposters can be done to different degrees of success, and sometimes we see examples of what is called popping, when either the transition from imposters or billboards to full geometry is very noticeable, or when stand-ins have not been used at all and objects pops into existence seemingly from nowhere as the viewer gets close enough for the object to be rendered.
Here's an example of popping from Watch Dogs. As you can see, the view distance is fairly short, which results in cars popping out of nowhere. This is to reduce the GPU load, but ends up being an issue because you are not always able to react to the cars that came out of nowhere. This would have been a great place to incorporate billboarding. The use of billboard health bars and name tags can be seen in a lot of video games, an example of which could be World of Warcraft.
When working with billboards, it is usually not a standalone solution. It is often used in conjunction with other methods to represent different levels of detail depending on different view distances to solve the problems of proximity and processing power for multiple objects in a single scene.
The proximity problem comes down to the fact that simple billboards become very obvious up close, especially with moving cameras, as the movement of the billboard will be visible in the scene rather than a hidden solution. In papers such as Rendering of Forest Scenes by Paul Guerrero, we see ways to categorize objects of varying distance and have their level of detail lower as the object gets further from the camera in order to improve performance.
Billboard clouds is an extension of basic billboarding originally created by Xavier Decoret and is similarly a method for rendering objects, but in a less taxing way computation-wise than full geometric objects. The way that billboard clouds differs from normal billboards are in that they don't rotate with the camera but rather creates a 3D representation of the model with image planes on the major surfaces of the original objects.
These representations will often be able to stand in for the original full geometric model up to a certain viewing distance, but will start to show its lower quality and lack of depth when seen from up close and from certain low angles. One of the benefits with this method is that in comparison to normal billboarding, you will not run into occlusion errors and the figures will have more depth.
Billboard clouds also have the added benefit of having a more complete representation of the original model, meaning that the figure will even look passable from high angles, which is usually a weakness of the flat billboard, as it either bends the model back to face the camera or exposes the edges of the billboard depending on the method implemented, it being either with or without Y-locking.
In the paper Tree Rendering with Billboard Clouds, Ismael Garcia, Mathias, and Laszlo Shermai-Kallas looks at the billboard clouds method and defines different viewpoints of objects in computer-generated environments, and proceed to work on trees as their object with a focus on leaves and how to use parallaxing effects and accurate occlusion to make better billboard clouds, while keeping the needed processing power low.
Billboard clouds have since been used and tweaked by many different people with various results. One group of researchers went into extreme model simplification for forest rendering. Anton L. Furman, Eike Umlauf, and Stefan Mantel made changes to the Billboard cloud algorithm in order to pack all textures of the Billboard cloud into one large texture in order to reduce texture switching.
Displacement map billboard clouds is another direction within the subject of billboard clouds. Stefan Mandler, Stefan Jeschke, and Mikkel Wimmer wrote an article on this, where they use billboard boxes instead of rectangles, with each box representing a volumetric part of the model. This procedure produces better results than regular billboard clouds at the cost of processing power, and is a good middle ground between looks and performance. This technique is very well suited for real-time rendering of places with a lot of complex objects in close proximity. Berendt Kolditz Franske Kopf and Deussen wrote a paper called Realistic Real-Time Rendering of Landscapes using billboard clouds, in which they demonstrate their technique of rendering large scenes in real time using shell textures. Shell texturing involves creating mesh layers, then using one or more alpha textures to create the effect of volume.
An example of the use of billboards is SpeedTree. SpeedTree, as they describe it, are a powerful toolkit used to create 3D animated plans and trees for games, animations, visual effects, and more. Their free Unity packages feature multiple level of details, including our billboard shader.
This is an example of SpeedTree in Unity. As you can see, the quality changes depending on the distance from the camera to the object. This clip also demonstrates one of the problems with billboarding, specifically when you look at the billboard from the top.
Here we have two identical trees. The tree on the right has its threshold for level of detail set lower than the one on the left. This means that the one on the right will have its billboard shader applied earlier than the one on the left.
We have here two examples of performance. The first one here, we have around 480 trees with a billboard shader. This results in around 70 to 80 frames per second.
This second example is similar to the previous, but with around 400 trees, but at a high level of detail, which result in it lying on a frame rate of 48 to 60 frames per second, despite there being fewer trees.
While trees and vegetation is a great way to demonstrate billboards, it is by no means the only one. Peter Lindgren uses spherical billboards to create smoke effects. Spherical billboards can help prevent the clipping issue of regular billboards.
There are others that have gone more into the use of billboards for lowering computation power and made comparison and benchmarks. An example of this can be seen in articles such as Real-Time Voxel Rendering, algorithm based on screen space billboard voxel buffer with sparse lookup textures by Simon Jablonski and Thomas Martin.
For our example shader, we have decided to keep it simple. Here, we're using a simple billboard shader from Wikibooks, which we're going to go through line by line.
First we have the name of the shader and where we can find it when you wish to apply it to a material. Next is the properties. These are the variables which can be changed in the inspector. Main text takes a 2D image. This is the billboard texture.
Scale X and scale Y is used to scale the billboard, if you want to make it larger or smaller. Subshader indicates that this is where the shader starts. pass indicates that a new shader pass starts here. This particular shader only has one pass.
CG program indicates that the language changes to CG instead of Unity's shader lab. Pragma is a line of code that tells the compiler to follow special rules and is in this instance given special orders in regards to vertex, vert, and fragment frag. Vertex are rules on how to alter vertices, while fragment is special rules on how to alter colors for the individual pixels.
Uniforms do not change from one execution of a shader program to the next within a particular rendering call. In Unity it is redundant, but it allows you to use the shader in other programs like Maya, etc.
The struct for vertex input defines the information on the vertices of the original model and stores both the vertices and the texture coordinates as 4x4 float matrices. And hereafter, the vertex output struct holds the altered position and texture.
The next part here is the vertex shader. What happens here is the origin matrix 0, 0, 0, 1 is transformed with a model view matrix, Unity matrix MV. We then subtract a matrix containing vertex x-axis inputs and vertex y-axis inputs, 0 and 0.
Then we multiply the matrix with scale x, scale y, 1 and 1 in order to be able to change the size of the billboard without affecting the original cube. Finally, we transform the results of this with the projection matrix Unity matrix P.
Here the input texture doesn't change and is just forwarded to the output. This is the end of the function, returning the output position and an unchanged texture output.
This is the pixel shader. This starts the function that goes in and changes the coloration based on the vertices of the output resulting from the pragma fragment frag from earlier.
Here it returns the changes made based on the original input 2D texture. Finally, end CG indicates the end of the CG language and in this case also the end of the shader.
This is the billboard shader in action. We have made a demonstration scene in Unity where we have 3 boxes. The blue box has a billboard shader attached to it, and as you can see, it follows the small white box.
When the 2 small boxes move behind the big box, they both get obscured. A shader would be well suited for a floating health bar or a name tag attached to a character in a game.
We have shown several examples of how billboards can be used. Both research material and application in games have been covered.
What we have found during our research is that billboarding, despite it seeming like a lo-fi and primitive solution, is still a method used in many modern games and other computer-generated imagery.
Billboarding will likely continue being used until GPUs become so powerful that you can render hundreds and thousands of polygons in real time. Until that day, we have to make do with billboards and imposters.